So most of the language we use to describe Boolean expressions comes from Boolean functions or Boolean operators. So first off, you might remember the word function from high school. A function, as in like a mathematical function, is something that takes in inputs and returns outputs. So if I have some function f and it takes in two real numbers x and y, then the function might return two lots of x plus y, right? And then I could like put something into that function, f of 3 and 5, and the output of that will be two lots of 3 plus a 5, which is 6 plus 5, which is 11. Okay? A Boolean function is much like the functions you've seen before, but this time it takes in and returns Boolean inputs and Boolean outputs. So if I let boldface b be the set containing true and false, then I can have a function f that takes two Booleans, that is, it takes two true or falses, and returns one true or false value. Now there's not that many combinations, so I can describe my function either as like an English statement, or using Boolean operators, which we'll get to in a moment, or I could describe it by like enumerating all possible combinations of inputs. And by enumerating all possible combinations like this, we call this a truth table, because it tells us all the possible options that the function can output given some inputs in a big table. And truth tables are useful for checking if two Boolean expressions are equivalent, which we'll see in a bit. So for example, if we look at this truth table here, it looks like the function only outputs a true when exactly one of the inputs is true. So for false, false, we get false. For false, true, we get true. For true, false, we get true. And for true, true, we get false. So I could describe the function f either as this table or as the simple English description f of xy is true when exactly one input is true. Okay? It doesn't really matter. Boolean operators, well, much like we have operators in algebra, they are arithmetic operators, plus, times, divide, square root, all that sort of thing. Boolean operators are operators that take in Boolean variables and then do something to them. So the first operators I want to introduce is the AND operator, which we denote by a little hat pointing upwards. The OR operator, which we denote with a little hat pointing downwards. And the NOT operator, which we represent with a little sideways L. You might see alternate symbols for these in other courses, but these are the symbols we would use. I'm going to describe the action of these operators by giving you a truth table for all the possible combinations. So AND is an operator that takes in two inputs. So I'll call the first input x, the second input y, and the output x and y. You'll note I put the AND symbol in the middle because it's an operator. Just like I could write like x plus y, or x times y, or x to the power of y. I guess that one doesn't really have a symbol, bad example, x minus y. Here, these operators are just kind of like functions that take in two inputs, but we put the symbol in the middle. So let's enumerate all the possible combinations. False, 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 true, true, false, true, true. And here's the truth table for false, for AND, I beg your pardon. So the AND operator is only true when the first input is true and the second input is true. It's only true when both inputs are true. When x is true and y is true. That's why it's called AND, right? So true when both x and y are true. Okay? Let's have a look at the OR operator. So the OR operator is a little bit different, but we use it in a similar fashion. And here's the truth table for the OR operator. And here you'll see the first distinction between the notation used in logic and the notation used, like the common English definition of the word OR. So I write out the truth table: false, 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 true, true, false, true, true. false, true, true, true. So here, the OR operator is true when X or Y is true, or even both of them. Now normally when you use OR in plain English, you really mean one or the other, right? If you go to a cafe and the waiter says you can get tea or coffee and you say both, that's probably not the answer he's looking for, right? But in logic, when we use OR, we mean one or the other or both, right? So you've got to be careful between the logic definition of OR and the plain English definition of OR. So true when at least one input is true. Okay. And the final operator we're going to talk about for a moment, the NOT operator. It only takes in a single input and it returns the opposite or the negation of that input. So we take in a single input X. If X is false, then not X is true. If X is true, then not X is false. Okay? So basically it negates, does the opposite of the input. And these operators are very useful because we can put these operators together to make complicated expressions. Okay? So it does the opposite of the input. Okay? So much like in algebra, I can make a complicated statement with lots of pluses and minuses and times. In Boolean algebra, I can make an expression by using lots of operations together. So I could have X and Y or Z. And by using brackets, I can sort of reduce any chances for ambiguity, right? Because if X and Y and Z were some predicates, this statement here, with the brackets on this side, would mean something different to this statement here. If we go back to our previous example about tea and coffee, this statement here could be, I would like tea, and I would like a slice of carrot cake or a slice of chocolate cake. So you're asking the waiter to bring you a cup of tea and one of the two desserts available. Or technically both, because again we're using logical law. This statement here reads differently, right? I want a cup of tea and I want a slice of carrot cake, or I want the chocolate cake by itself. So these two statements are different because of the bracketing, right? And so by adding brackets, that's one way to get rid of the ambiguity in such statements.